which is from our sensors, which is from our, what I can say, the different types of drones, the robotic field, all these information that has been taken need to be analyzed to convert this into a useful decision. So today our focus is how these machine learning can help us to predict, deduct, and decide. How can we predict? How can we deduct something? How can we decide based on the information that we gain? Right? So if you see over here, this is a 6 lesson journey. In this diagram that shows how different technology in this course work together. So sensors provide the foundation because they collect information about soil, weather, and crop data. Then we have something called as computer vision that allow artificial intelligence to see what is happening in the field. Then the robotics and the automation allows the system to act physically. And then the today's topic is a crop prediction and decision making that act as a brain to those technology. So in this slide, we are trying to connect of what all we have learned and how we are moving. Right? So what is a decision making? For example, if we have a soil sensor may report that is moisture is low, then this measurement is what I can say required to make a decision that must be determined whether the farmer should irrigate now or wait for the rain to be expected, or it should irrigate only one section. So the lesson from 1 to 3 gave us the raw information and the physical capabilities. Lesson 4 is going to transform that information into recommendation. At the end of today's lecture, you should be able to explain how that transformation happened. Moving on to our third slide, these are the learning objectives that we will see. First, we will understand the basic predictive analytics process from collecting data to taking an action. Second, we will examine what real agriculture data looks like. Then third, we will see how the machine learning models can recommend crop, predict yield, and identify plant disease. Finally, we will consider whether these systems are always beneficial. We will discuss these questions involving sustainability, farmer trust, privacy, and access to technology. Right? So this is how it has been classified in this slide as A, B, C, D. Now, let's begin with the central concept of predictive analysis. So can anybody tell me what is predictive analysis, or do you have any idea of what is predictive analysis?
Predictive analysis is a data analysis technique which is uses past and present data to forecast future agricultural outcomes and such as crop yields, pest attacks, disease, outbreaks, and irrigation needs. Then
Yes.
I think it's also work like data is collected from like soil sensors, weather stations, drones in as we know as previous classes, satellites farm records, AI and ML analyze the data, and the system identifies pattern and predict future conditions, and that's only, and farmer receive also recommendation for the action. That's it.
Yes, yes, that's absolutely correct. So, a predictive analytics or a predictive analysis is nothing but it uses a previous data to estimate what is going to happen in future. Now, let us try to understand this with the help of example. Consider a farmer who has a recorded rainfall, temperature, fertilizer use, soil quality, and crop yield for 10 years. Now, a machine learning model can study those historical patterns and answer questions such as what yield should the farmer expect this season? Which crop is the most suitable for this particular soil that the farmer has? Is a disease outbreak likely to happen? Should the farmer irrigate today? And when is the best time to harvest? The slide shows the 5 step pipeline, but rather than treating it as 5 isolated boxes, let us consider this with the help of one example. Imagine that we want to predict a rice yield. First, we will collect the information. That's the first pipeline. Okay. We will collect the information from the sensors, weather services, satellite images, and farm record. Second, we clean that data. That means we are going to remove the unnecessary sensor failures. The values may be missing, and there are different systems that may use a different measurement unit. So we are going to organize that in one format that is called as cleaning. Third, we are going to train the model using the past example. Then the model learn relationship between environmental condition and crop yield. The fourth one is we provide a new condition and ask the model to predict, right? The model may estimate that the farmer will produce 4.7 ton per hectare. And finally, the farmer must act, and the farmer may adjust the irrigation, applying of fertilizers, delay planting, or decide that no action is necessary. The final step is critical because AI is useful when its output can support an appropriate action. This is a five-step pipeline in which what we are talking about collect, clean, train, then we are talking about act.
Yes,
Now,
ma'am.
prediction and decisions are not exactly the same thing. A prediction says there may be a rain is likely tomorrow. A decision says do not irrigate today. So there is a difference between a prediction and a decision. Decision is something that you take. Prediction is that the chances or the likelihood of things to be happen. That is what a prediction means. Right? Now let us connect this process to the technologies we have studied in previous lessons. Moving on to next slide, that is slide number 5. Now, this workflow connect nearly everything what we have studied so far. On the left, you see a sensor that collects the values such as soil, moisture, temperature, humidity, pH value, and the leaf images. The information is stored in the database or a cloud system. The machine learning model then look for patterns. The model does not simply return a complicated table. A useful agricultural system converts the model output into a clear recommendation. Then what's happening? Then something is going back that is called as feedback, where based on the feedback, again the new sensor is going to work. It is going to store the information in the database. Then the machine learning is going to take the patterns, and then it is going to give us the information to act or make a decision. Now, one of the most common agricultural prediction tasks is estimating a crop yield. Okay, so we are going to talk over here about a crop yield. Now, what do you see about a crop yield over here? Let's try to understand this slide, then I will take you over the real data set. Okay. Now, crop yield prediction asks a numerical question. How much crop will a field produce? Because the answer is in numbers such as tons per hectare, and this is usually a regression problem. The model over here uses a rainfall, temperature, nitrogen, phosphorus, potassium, soil, pH values, um, previous yield, satellite vegetation information, fertilizer use, and irrigation type. So these were the things the model considered. Which model? Machine learning model considered all these information in order to predict what type of grain that is, right? Now let us try to understand with the help of example that if we have two farmers, farmer A and farmer B, farmer A receives sufficient rainfall and has a balanced soil and nutrient. Farmer B experienced low rainfall and has a poor soil nitrogen. Even before the harvesting, the machine learning model may predict that farm A will produce higher yield because it has a sufficient rainfall and a balanced soil nutrients. So this information can support several decisions. A farmer can estimate income before harvesting. Food distributors can plan transportation and storage. The government agencies can estimate whether a region may experience a food shortage or no. So, however, we must be careful with a very high accuracy claim, right? So, how each thing is dependent on another. A model may perform extremely well on a control database but perform differently on the real farm because real farm has a weather condition change, sensors may be inaccurate, and a new farm may differ from the farm that is being presented in our training data. We will discuss now with the help of example. Let me show you a real data set of how we made this prediction of a crop yield. Okay. So have you heard about something called as Kaggle dataset? Do you see the Kaggle dataset over here or the slides? Kaggle dataset, right? So this is a real-time data which you can download, okay, from here. Now this data has a data card. This is how the dataset looks like, where you have nitrogen, potassium, then something called as phosphorus, potassium, nitrogen, temperature, humidity, right? Then if you go down over here, you have something called as pH values, rainfall, and then a label. So if you see this example, the very first example, based on all these information, the machine learning predict that this is rice. Okay? Then maybe with some other prediction, it predict that this is maize. Does that make sense? Then some other prediction, it predict that it is a chickpea. So based on what? Based on the information that the machine is training, it considered the features or the data field as nitrogen, phosphorus, potassium, temperature, humidity, pH level, and rainfall. So all of these features machine learning consider in order to predict or in order to say that this farm is a rice farm, this is a crop, or this might be maize, this might be a chickpea, right? So you can plant based on all these field, this farmland is best to harvest chickpea. This farmland is best to harvest rice because of these features. What were the features that were considered? The considered features were the nitrogen, ratio of nitrogen content in the soil, ratio of phosphorus content in the soil, ratio of potassium content in the soil, temperature, humidity, pH value of the soil, and the rainfall. Now we are going to see something called as disease detection system. A disease detection model receives an image and predicts a category. So the first model, what we have seen, the model which we talked about by taking a data set, considering the features or the values, okay, based on the input feature, it has predicted whether we should, based on the soil, the temperature and everything, which crop that we can harvest, whether it is a rice, wheat, maize, chickpea, or whatsoever, right? That was the first thing. Then the second model is predicting something called as disease detection model that receives an image and predict the category, whether this leaf is a healthy leaf or it may be classified as an unhealthy leaf or a what I can say early blight, late blight, rust, leaf spot, right? So for us, if we are talking about a layman, we will see if a leaf goes bad, we will say it is unhealthy. But what kind of unhealthy that is? I mean, is it an early blight? Is it a late blight? Does it has rust or it has a leaf on the spot? This is being done with the help of a supervised classification because the training images are already have labels. So during this training, the model see thousands of example. It gradually learn the certain kind of a color, shape, edges, texture, and associated with the particular disease. We are going to see the actual, what I can say, how the machine learns. I'm going to show you in a minute. Okay. Then the farmer could take a photograph with the smartphone and receive the possible disease classification within the second. And however, the model answer should be treated as a decision support, not as an unquestionable diagnosis. The poor light, unusual camera angles, damaged leaf, and diseases not represents the training data and can affect all the result. So when you are taking a picture of any of the leaf and trying to understand what type of disease that leaf has, you need to keep in mind that the poor lighting, unusual angle of the camera, the damaged leaves, and you're not taking a complete picture of the leaf, the farmers are not taking complete picture of a leaf, then it is going to affect the entire result because you're going to train the model, not the complete information. Does that make sense? So if you see on the screen, you have something called as corn common rust, potato early blight, tomato early blight. So these leaves. So the first one over here is the corn common rust. The second one is a potato early blight. The third one is the tomato early blight. Then the fourth one is a corn northern leaf blight. And the fifth one over here is a potato late blight. And the sixth one over here is something called as tomato leaf mold. Now, these six classes are frequently used in machine learning and computer vision dataset for a crop disease detection from the leaf images. Anybody classify what we have done in the previous slide, crop yield? What the machine learning or how the machine learning was helpful over here? Here in this slide, we have seen that the typical features were considered in order to predict. Then in the second slide, we talked about the disease detection system by taking pictures and making our machine learn using pictures.
Ma'am, please repeat.
I said in this slide that is called as crop yield prediction, we have seen a prediction based on the features, right? Some of the features we have considered, and based on that, we have predicted that particular soil is good for rice. The particular soil is good for wheat. The particular soil is good for maize. The particular soil is good for chickpea. Then in the second slide or the seventh slide, I can say we have discussed about disease detection method. That's another, what I can say, feature of a machine learning where we are saying that we are going to train our model not only for prediction, we are going to train our model to identify what type of disease that this leaf has by taking pictures and training our model and seeing whether this leaf is going to if we are going to spray the nutrient, is it going to go good, or is it's like so bad that it is not going to be useful. Does this make sense?
Yes, ma'am.
Now, how does the model actually sees the disease? Now, when a human examines a disease leaf, we may notice a yellow area, a dark spots, the holes, and an unusual edges, right? This is what we see, and we completely say that the leaf has gone bad. Now, computer does not understand those concepts or these concepts. So it begins with the pixels, right? Our eye is entirely different than what computer sees. So computers try to map with the pixel. Each layer of the neural network deducts a simple visual pattern such as edges, line, color, right? Now, deep layer combine those pattern into a meaningful structure such as leaves, veins, lesion, and disease spots. The heat map shown on the slides represents the image region that influence the model most strongly. In this example, the model focuses on the damages area rather than the entire background. So this type of visualization is helpful because it helps us to evaluate whether the model is paying attention to the correct part of the image or no. Or the image that the model predicts a disease is correctly but focuses on a label background, object, or the photograph hands, or that would suggest that the model learn have gone wrong. It is also important to distinguish a disease from a nutrient deficient. Now, cellular lesion may indicate that it is a fungal disease. Uniform yellowing may indicate it is an insufficient nitrogen. If the system confuses between these two problems, then this would recommend the wrong treatment, right? Everything that is yellow is not that your leaf required nutrient or it does has a fungal disease. There are two different things. A circular lesion, meaning a circular form, is something where it is a fungal disease. When it comes to a uniform yellowing, it may indicate an insufficient nitrogen. So spraying nitrogen on those areas is going to help the leaf to grow more, or to help the leaf in order to get it in a good condition. Does this make sense to you people?
Yes, ma'am.
Now, let me quickly take you to a place where I was talking about. So this is Get Start. Okay. I want to have an image project. I'm going to use this. So let's say it is a healthy image. Okay. Then I have another class that is called as unhealthy image, because most of you, are not very much familiar with the program. This we can have done with the help of a Python program, but I thought it is easier to have our image transmission. Okay, so from outside of my garden, I have taken these two leaves. Okay, do you see that I am recording that this is what my sample looks like for the leaf. Okay,
Yes, ma'am.
Yes, ma'am.
are you
Yes,
able to see
ma'am.
that? Okay,
Yes,
amazing.
ma'am. Yes, ma'am.
That was for the healthy leaf, right? Now I'm gonna do the same thing for my unhealthy leaf. I'm gonna train my machine that this is what an unhealthy leaf looks like. Okay, right? Then I'm gonna train my model saying that this is what a healthy image is, and these are the unhealthy images, right? Now this is training. Do you see that the model is being trained?
Yes,
Yes,
ma'am.
Right?
yes,
So
ma'am.
this were the unhealthy image and this were the healthy image. Now let's see. I am going to show this. That can you classify what is this? What does it says? What does it says?
Model is trained.
No, no, the model is trained, but what output we are getting? Is this a healthy image or it's an unhealthy image? Right? Right. Let's see, try with the unhealthy image. What does it says now?
It is unhealthy.
Unhealthy
The
image.
image.
Unhealthy image.
Absolutely. Right? So how does this, what I can say, computer knows about it? Because we train with the help of models, right? We train with the help of images. Likewise, the hundreds and thousands of images are being trained to the model that this is what a healthy looks like, this is what unhealthy looks like, this leaf maybe has a fungal infection, this requires a nitrogen deficient. So all this information is being shared and trained to the machine so that the machines can able to deduct whether this is being classified. So based on this particular model, if I'm gonna bring some other like leaf, okay, this is some other leaf, maybe it's not fully gone bad, so this is another leaf. Now you see the prediction says that the image has like a 70% of healthy, and remaining other percentage like a 30 and 40 percentage is unhealthy. Do you see this? So that's how we classify. This is a third image that I have. This is a fourth image. I am classifying this because I trained these two. Now I am trying to classify what happened with these two. Were you able to understand?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Do you see the screen now?
Yes, ma'am.
Yes,
The slides?
Yes, ma'am.
Okay.
Ma'am, but I have some question.
Yeah, please go ahead.
Ma'am, so I will train machine to examine or but ma'am, how will we teach the machine that this plant is 50% healthy or 30% unhealthy?
Because I have used a different type of what I can say leaf. I trained my leaf with a healthy
Ma'am,
leaf and an unhealthy leaf.
but ma'am, how I can identify like this plant, this leaf is 30% only unhealthy and this is 50% healthy. How I can identify? Firstly, I can identify. Then after machine will I will train to machine.
No, not you will identify. The machine is identifying itself. That's why in the previous, what I can say, slide, I told you that we human can see only this part, that this is black, and that's why the leaf is not good. But how much percentage? How can you say that this is 70%? We cannot say by our own eyes, right? How can we classify that this is 70%, 60%? But whereas the machine will see like this, it will see the edges, the veins, the roots, the small veins, right? And the lesion heat map. You
Ma'am,
see, where does it goes back?
I think like this sensor AI modes do not see like the humans, but it sees like image and like grid of numbers like pixels, learns pattern that
Yes,
associated with the
yes,
healthy or disease plant.
yes, absolutely. Yes, that's
Oh,
correct. That's correct. Absolutely. Okay. Any other questions?
no, ma'am.
Okay. Now we are going to talk about pest monitoring from sky. Now, in this slide, we are going to see how the artificial intelligence or a machine learning is going to help us seeing something from the sky, from the drones. Okay. So, inspecting one leaf is useful, like how we have seen in our demo. But farmers may have to manage hundreds and thousands of acres. He cannot train like each and every leaf, like this is how the wheat looks like, this is how rice looks like, this is how chickpea looks like, right? It's next to impossible because farmers will have a bigger land. So it would take a person a very long time to examine each row manually. So what they do, a drone can fly over the field and collect RGB. What is RGB? Can anybody tell me what is RGB?
Red, green, blue.
Yes, ma'am.
Absolutely. Absolutely. Excellent. That is called as red, green, blue or multispectral images. The artificial intelligence system analyze those images and create a map showing a healthy areas that could be washed and high risk pest location. The farmers can then spray only the affected zone. This is called as a target or a spot spraying. The advantage is not only simply a speed, but also the target spraying that can cause a chemical use, lower the cost, and limit the unnecessary exposure for beneficial insect and surrounding ecosystem. So if you see over here, AI drones in Maharashtra, right? And then John Deere sea spray, that is in United States. And if you see the maps over here, from the drones, the field looks something like this. What is this? The yellows are the ones that is like a kind of an attention area or something to watch. The red ones are the hotspot that requires attention, and the green ones are healthy.
Yes, ma'am.
Now, something that could affect this technique is a weather prediction. So the pest data is only one input. Then the weather prediction can also change what farmers should do, right? So these things must go hand in hand. Now we are going to move about weather forecasting prediction. Now, traditional weather forecasting uses a physical-based numerical method. These models stimulates the atmospheric process such as pressure, wind, temperature, and moisture. But the modern machine learning system can complement those models by learning from the historical weather pattern and correcting a certain forecasting error. Now, for a farmer, the most useful forecast is not always a long term climate average, but for the farmers, they may need a practical answer for next 24 hours and 72 hours. If you remember in the olden days for our parents and grandparents, we do not have something called as weather forecast. Do we have weather forecast? No. But now we have a system called as weather forecast wherein people, in the news channels or maybe an SMS alerts, we get an information that in the next 24 hours, there is going to be a rain. There is going to be a storm. There is going to be a flood. So, how these things are happening? These things are happening based on machine learning or the prediction model that will predict that it is going to happen or the likelihood of happen based on the information that they have. Now, we have something called as AI-based decision support system. Now, what happened with this decision support system is this will combine the multiple sources of information and produces one understandable recommendation. Now imagine that the farmer is deciding when to irrigate. The soil sensor reports low moisture. If we considered only that signal, the answer would be to irrigate. However, the weather condition or the weather model predicts that it is going to rain heavily tomorrow. The crop model indicates that the plants are not under serve stress. The water cost information shows that the irrigation is expensive today. Now, the decision support system bring all these signals together and may recommend waiting for the expected rainfall. The most important idea is that no signal model has the complete answer. One model predict yield, the another detect disease, the another predict weather, the another model predict market price, the another evaluate soil irrigations or the soil health. So the decision support system integrate these specialized outputs into one recommendations. So what do I mean by this? I mean that the all information or the decision that needs to be taken is based on the entire field. It's not just that your soil is moisture, it is best to irrigate. The weather model shows that it is going to rain tomorrow. So what we have to do? We have to consider everything. We have to consider each and every model, and based on consideration of all these factors, we have to take a decision, right? Not only one model is going to predict everything. One model is going to detect the disease, like how I showed you with the images. The other model is going to predict the weather. The another model is going to monitor the market price. The other model is going to evaluate the soil health. The other model is going to tell us which soil is best or which land is best to irrigate what crop or what has to harvest which crop based on the Kaggle dataset that we have seen, right? So the system should also explain its recommendation. A farmer is most likely to trust the message, wait to irrigate because 30 milliseconds of the rain is expected tomorrow, than a message that simply says do not irrigate. So a AI recommendation system has to explain or send a message in a way that not just say do not irrigate, but wait until 30 millimeters of rain is expected tomorrow. So wait that rain has passed and then you can go for irrigation. Does this make sense to you people?
Yes, ma'am.
Yes, ma'am.
Okay. Now moving on, AI cuts waste, not yield. Now, what are we talking about in this slide? We are saying that the conventional agriculture often uses a uniform approach. The entire field may receive the same quality of water, fertilizers, and pesticide. However, fields are rarely uniform. One section may be dry while the other section already has enough moisture, right? We have seen this type of example in our last classes as well. Now, one area may have a poor nitrogen while the other has a sufficient nitrogen. So you cannot consider the whole farmland as one. Now, AI-driven decision or precise agriculture treat the field as a collection of smaller zone. Water can be applied on a moisture level, fertilizers can be adjusted according to the soil test and plant health indicators, and pesticides can applied only where the pests or the diseases are detected. The goal is not simply to use less of everything. The goal is to use the correct input in the correct place with the correct time, right? So this is why this slide emphasizes on reducing waste without reducing your yield. Now, if I have to ask you a question, what happens if the recommendation is technically accurate but the farmer do not trust it? Yeah. What happens if the farmer is not going to trust the decision that was or the recommendation that was technically accurate but the farmer does not trust? The sustainability benefits or the sustainability benefits exist only when the recommendation is understandable, affordable, and practical. So we need to gain a trust, or the farmers need to gain a trust in order to adapt to these new technologies, right? Now, in the next slide, we will see how the different countries are building these agricultural AI system in different ways. Okay. The first one is an AI meets Bharat field, where in Indian agricultural AI effort depends on public digital infrastructure, government agencies, research institutions, and partnership. Some of these institutions are like Indian Council of Agricultural Research, Foundation for Policies and Researches in India, then Digital Agricultural Stacks, then Core Agricultural Registry. So these are few of the firms and the government agencies, research institution, and the partnerships where we are following them for AI or enabling AI. The system, such as agricultural stack, aim to create a shared data foundation involving farm identities, land information, crop records, and agricultural services. So all these database, like a kind of a database for the Indian agricultural system, you can find it in agricultural stack. For an AI system, this is a shared data layer, which is an important thing because the model needs a consistent and an organized information. The knowledge check question asks about agricultural stack's primary role, and the best answer is to provide as a unified data layer. Right? So from there, we are going to fetch the features what is being required. This is like a kind of a database from where you will have a shared foundation of involving all the farm identities, land information, crop records, and agricultural services in the agricultural stacks. Right?
All right.
Then we are comparing this with the United States. United States has somewhat different agricultural technology. They have something called as United States Department of Agriculture fecal year. Then they have National Agricultural Statistical Services application program interface APIs. Then they have farm artificial intelligence, and then they also have a National Institute of Food and Agriculture. So in United States, agricultural AI is often driven by the private technologies, companies, equipment managers, and farm management platforms. So they do not have any, what I can say, direct involvement with the government, but they do have like government agencies that contributes through data sets, research grants, and national agricultural statistics, right? So India's approach has a strong public infrastructure components, and the United States rely most or heavily on the private sector platform supported by the federal research and the open data. So this is like a kind of a transition between these two countries, how the AI is being implemented. The next two slides are going to be in kind of an activity. If you remember the Kaggle slide, which I have showed you, the Kaggle data set. Now, this slide summarizes the problem that we examined with the Kaggle demonstration. The model receives 7 inputs. As you can see, what were the 7 inputs? If you remember, nitrogen, right? Phosphorus, potassium, temperature, humidity, pH, and rainfall. Now, if or it then selects one crop from a 22 possible categories, the first few rows shown on the slides are labeled as rice, right? Notice that these are not identical. What do I mean by this? They are not identical. If you see the pH value, it is labeled as rice as 6.50, but at the third time, the pH value is 7.84, but still it is considered or labeled as rice. So machine learning does not require every rice example to have exactly the same value. Instead, it learns the approximate combination and ranges associated with each crop. So this is an important, what I can say, distinction for a real agricultural conditions that are not perfectly identical. Does this make sense to you people? If you
Yes,
see
ma'am.
on the slides, these informations are not identical. They are not same, but still they are labeled as rice, right? So what is that we are concluding? The key takeaway is that not all the information that is being shared or the features will have the exact same value to identify or classify or label as this is a rice or this is a wheat or this is a chickpea flour, right? It varies on a different condition. Machine learning does not have or need to have an exactly same value. It is going to consider the approximate combination and the range, right? So it's going to consider the range, not the exact value. Like for example, between 200 to 270, it is going to classify it as rice. So if you see over here, the rain claims is 2.20 mm, here 263, here 242, 262. It is classified as or labeled as rice. Now, this is something completely based on what I can say a programming language that is Python. If you're familiar with it, you can definitely try to run these methods, or I can say the program, and then you can see how we are classifying this as a rice, how we are classifying this as um, some other crop, maize or chickpea, right? For that, the steps are being given over here. You need to build a CSV file. You need to download that file, which I have showed to you. Then you need to explore this. You need to visualize this, meaning considering the features. Then you need to split it into 80 and 20. If you remember, I told you 80% of a data is going to train and 20% it is going to deduct. You have to train or split your data into 80 and 20. 80 you will train the model and the rest 20 it is going to predict by itself, right? And then you will train the model and predict the new farm. Make sense?
Yes.
Yes. Now, this slide represents the more advanced version of what we have created in our teachable machine, demo. A production model may classify multiple crops and several disease categories. Before the image is also entered into the model, it resizes into a consistent format. Then the neural network process the image and produce the probability or the possibilities for each possible class. The system then display the category with the largest or the highest predicted possibility. The key difference between these two demonstrations is the form of input. The crop recommendation model uses the rows, columns for the numerical values, whereas the disease detection system model uses a pixel. Despite that the difference, the general machine learning process remains simple. That means it's going to collect the sample, label them, train them, test the model, and then use it carefully. Right? This is a more advanced level. If you see, it has a classes to use today. That is going to be tomato early blight, tomato late blight, tomato healthy, potato late blight, and potato early blight. These were the images that were trained. Right? This is a no-code alternative that is called as machine teachable. I have given over here, you can check in the slide, and you can train anything by classifying or the demonstration that I have showed you. Now, what the model got right and wrong. Now, this table is important because what I can say, it reminds us that the AI predictions are not always correct. So what is that we are trying to see over here? Most of the examples, what we have classified would be correct. However, one potato leaf with the late blight was classified as a tomato leaf with the late blight. Do you see? The results are correct, 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 wrong, and then correct. Right? Now, the two plants may show visually similar disease symptoms because they are same or a related pathogen and they can produce a similar lesion. So the model may correctly recognize the disease pattern but incorrectly identify the plant species. Instead of what I can say, potato, it has been classified as tomato. So this example shows that we must examine more for our overall accuracy. So which class are being confused? Does the error create any serious risk? Is the model equally accurate across different crop? What happens when the confidence is low? And a wrong prediction with 58% confidence should be treated differently from a prediction with a 99% confidence. Meaning, when something we are achieving 99%, we should focus more on that. Instead, the wrong prediction is 58%. So, a practical system could respond by saying that the result is uncertain. Take another image or the consultation on an agricultural specialist wherever the model is going to give you something wrong or something which is unpredictable. What you need to remember from this particular lecture is there are 5 things that you need to remember. First, the predictive agriculture requires 3 things. What does it require? It requires data, it requires model, it requires decision, right? Based on your data and model, the decision would be taken. Then collecting a data without using it does not create a smart farm. Second, the data set are the fuel of machine learning. So that means if you are going to have a correct data set, then you are going to predict the good result. A powerful model trained on incomplete, biased, or inaccurate data will still produce a poor result. Even though the model is good, but you are not training that on a very good data, on a very accurate data, right? The third thing is AI can support several agricultural tasks such as predicting yield, detecting diseases, monitoring pests, forecasting weather, and recommendation actions, right? We have seen the example of all of these respectively. Then fourth is an agricultural AI can organize differently across region. India demonstrate a strong public infrastructure approach while the United States relies more heavily on a commercial platform supported by a public research and an open data. Finally, we also require farmer trust. That is something very essential in order to implement all these things that we have learned about. Right? Finally, a model may save water or reduce or pesticide use, but it does not have no real value if the farmer cannot understand it, access it, effort is, or does have a trust issues or the recommendations. So we need to consider all these, what I can say, features or all these important factors in order to enable this information, right? So out of this, what I have told you, which factor do you believe is the most important for a successful agricultural AI? Model accuracy, data quality, affordability, or the farmer trust? Which one?
Farmer trust.
Model accuracy.
Okay. So if you ask me, I will say there is no single perfect answer. All of the 4 are correct, connected, right? So we require a model accuracy to predict good. We require a data quality that needs to be good. We require affordability. If everything is good, but it has a lot of price, then Indian farmers cannot execute it. If everything is good, but farmer does not trust, then we cannot implement AI system, right? So there is no single perfect answer. All of these 4 things are connected, right? So to have a factor that needs to implement a successful agricultural AI, we need to have a good model accuracy, good data quality, it should be affordable, and we need to have a farmer trust, right? Then we have a slide that is called as reference and further reading. If you are interested in exploring more, you can read it from here. And these are few of the academic literatures from where I have collected this information and shared with you. These are the policy reports I have considered. This is the academic literature from where I have prepared these slides. And these are the databases which I talked to you about. The Kaggle recommendation, this is for the activity 1. You can download this data set. This is the second data set, and this is the third data set, right? So that's based on the crop recommendation. That's an agricultural production and yield, and this is a plant village data set. So these are the 3 different data sets. You can download them, and then you can also read about it. Any questions?
Yes, ma'am.
Please go ahead.
So, ma'am, you have told us that sometimes machines can predict wrong. So, what can be
Mhm.
the reason?
The reason would be based on the training itself. Like, for example, while I was training the bad leaf, I did not give the exact pixels, right? That could be one of the reason. The second reason would be if the 2 leaves have the same disease, right? And they look similar, that could be one of the reason. You get it what I mean?
Yes, ma'am. Thank you.
Welcome. Okay. Thank you for your attention. See you all next week.